Okay, so we are already 10 minutes into our session and I just hit record. So we've already covered this. So just briefly, we're going to look at continuity. We review limits. There's three ways of doing limits using a table, graphing, and the algebraic method where you only need to know two properties. And to find the limit, it's always two situations, one from the right and one from the what? Left. You
Left.
approach the same value and the y values are approaching the same number. But the key is for limits, you don't need to have a y value there. For continuity, however, yes, you do need to have a y value at x equals a. So to be continuous, you have to satisfy three conditions. Number one, the limit exists as x approaches a. Number two, there is a y value at what? At a.
And
And the limit and the y value happen to be exactly what? The same.
the
So it's something like this. You're approaching a from both what? Both sides.
side.
Uh-huh. And if I erase that right there, great. I erased the whole thing. So imagine it's something like that. Even though there's no y value, the limit exists because the limit is going to be this value right there. But it turns out, if you fill this in, now you have a y value at a. F at a equals, we'll just call that L for right now. And it turns out that the limit value and the y value are the same, but graphically it just means there's no breaks in the graph. Got it?
Okay.
So this graph is continuous. Now, most of the questions that you'll be asked on the AP test is based on an interval, like from here to here. They'll ask you, is it continuous from here to what? Here. Sometimes they'll say, is it continuous everywhere? That means from negative infinity to what? Positive,
Positive
yeah, infinity. Okay. All right. Now, if there is continuity, guess what? There is something called
discontinuity.
discontinuity. Okay. Now, it's very easy. It just means that there's a break in the graph. So, like, if you have something like this, is it this? Okay, does the limit exist?
Yes.
Is it continuous?
No.
So it is discontinuous at, we'll call this a again, at x equals what? A. Okay. Now there's different content discontinuities. For instance, notice this one. If you have a graph that looks like this, and it stops here, and then it starts. Let's say that the graph just continues like this. This is a piecewise function. Well, guess what? This is also okay. First of all, does this have a limit?
Yes.
No. Remember, to have a limit, it has to be the same on both what?
Side.
Yeah, you have to
Oh.
approach. Yeah, you have to approach the y value on both sides. So the moment a limit does not exist, it's not also well, it's no longer continuous. Okay. So if the limit doesn't exist, it's no longer what? Continuous. But they're always going to ask you some question like this. What kind of a discontinuous? What kind of discontinuity is this? Well, just think of it like this. You're walking and then you what?
Fall.
Well, you jump, okay? You jump. This is called jump discontinuity, okay? Jump discontinuity. Yeah. You can have something like this as well, where you're going like this, and then it starts up here. Well, you have to jump what?
Huh?
Yeah. So again, jump discontinuity. Okay. Now another type of discontinuity is something like this. Oops. When you have a graph and it's like this, but the y value is like right there. Notice you're not going to jump. Okay. Does this is does the limit exist at x equals a? Yes. Come on, man.
Wait. Oh. On point that it wouldn't be a limit, but since there's no lines, it is a limit.
Wait, what are you talking about lines? So all you have to do is this: as you approach a from both sides, you look up at the y values. They're approaching the same what y value here.
Oh,
Okay, here maybe this might even make more sense. Draw it like this. That. Notice if you approach a from this side, your y values are going to be right here, right? And then as you get closer and closer, what's going to happen to your y values? It's going to go down to what number though? Somewhere right about here, right? And if I approach a from the left side, I'll use a different color, like white. So if I approach a from the left side, notice my y value is right there, right? If I get even closer, my y value will be even what? Higher? And it's getting closer to that guy. We call that the limit. You see it?
yeah.
Yeah. So the limit exists, but is it continuous? No. So what happened? What do we call this? We call this a removable discontinuity. Okay, removable discontinuity. Now there's a few more. Well, I think there's one more actually. Now we have what you call infinite discontinuity. So let's imagine that we have a graph that does this. These are your asymptotes, and your graph does this. Okay. All right, and let's imagine that A happens to be also the uh, the asymptote. So as you approach, okay, first of all, do we have a limit at x equals a?
No.
No, very good. Because when you approach a from the right side, I'm sorry, the left side, you're gonna go down infinitely this way, right?
Yeah.
And as you approach a from this side, your y values infinitely go positive.
Um,
So we call this infinite what? Right, infinite discontinuity. Okay. Now, as I told you, it's just terminology, but you have to get clear on these words. You have to know exactly what they're saying, what they're referring to, because the teacher, when she starts teaching class, or he or she or whatever, he, she, or it, your math teacher, it could be an it, he, they,
so,
whatever pronoun they're gonna use. Oh, so dumb, right? Okay, they're gonna be like, blah 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 blah. They use all these fancy terms. You're probably going to be, well, if you didn't take the tutoring beforehand, you'll probably be just staring at the wall. All the words are going into your ear, out your nose, you know, and you're just like hoping to see some pattern that you can recognize. By the way, if you've been learning like that, that is the worst way to learn. Did you know that? It's the hardest to study for. Now, some people, they're really sharp, they can figure out a pattern, but to a certain extent, they'll know what to do, and after that, they'll just flop. Meaning, like during the test, the teacher gives you something else, and you have no idea what's going on. Anyways, you want to listen to every single word and know what every single word means. Okay, so there's three types of discontinuity. Well, number one, we have jump discontinuity, when you jump, right? And then there's the removable what?
Discontinuity.
Yeah, you just remove it and put it right there. I guess you could say it like that. And we have infinite discontinuities. Okay? All right. Now, proving that something is continuous or not discontinuous is actually fairly easy. So let's try some problems. Uh, yeah. So here we go. Okay. Now, can you read this out loud? This is the actual definition of something that is continuous. Go ahead.
A function f is continuous. But one f is defined at a, that is so that f is the limit of f of x exists. The limit of x is f of a.
Okay. Does that now make sense?
Not
Almost.
really.
Not really. Okay, try this again. Number one, f is defined at a. What does that mean?
Oh,
The function f gives you y coordinates. So this is another way of saying the y coordinate exists at what?
okay.
Do you get it? That's all. That's all it is.
Yeah.
Yeah. So
Okay.
what they're saying is there is a y value at what? At a. Okay, that is a is in the domain of f. So that f at a is a real number. It's an actual number, like a y value, right? Number two. Yeah. So that means, even though there's a hole, they're approaching the same number, right? Okay. Now look at the third one. Isn't this what I just said? The limit should be equal to the what? Yeah, meaning that the whole is filled up with a dot. Do you get it?
Mm.
Okay, now does that make sense? Yeah. Now, if I showed you this first and had you read it, you'll probably be like really just like I don't even know what's going on, right? But now the reason why these definitions are so important because most students when they study calc, they're trying to do the same thing with algebra 1. They don't care what the word stands for. They see the teacher move numbers left and right. They're like, "Oh, yeah, you could just subtract this number." And they just kind of like make up their own procedure. But when you take the AP Calc test, students don't realize that the AP Calc exam is always going to shoot after students who know what? This stuff here. Like on the free response, they'll say something like, prove that this is discontinuous or continuous. You have to say, well, condition number one, A, f of A exists. Condition number two, the limit exists. Condition number three, both are equal to each other. When the grader sees you make that list, they know you know the definition of it what?
The
Con
continuous.
yeah, or we call it continuity, okay? All right. Anyways, it's worthwhile to stop and really understand, what's being said here. Okay, now let's try some problems. All right. Okay, now this is really gonna hammer down on your ability to graph rational functions. So if you struggle a little bit here, we're gonna actually stop and do some graphing, okay? But go ahead and read it. By the way, is your internet connection kind of choppy? Am I
Um, no,
I'm not cutting in and out, right? My audio?
no, it's not completely.
Okay, yeah. Your video is kind of like what do you call it? Like
Okay.
it's
I'm
like
not. You're fine by.
okay, as long as I'm good on your end, yeah. And it is being recorded, so you can see this in more smooth, fluid, 4K experience. But you know what it feels like? I feel like I'm watching someone play video game at like 30 FPS. Okay, can you read out loud?
Determine whether the function f of x equals 2x plus 1 over 2x squared minus x minus 1 is continuous. A at 2 and B at
Like now, you're like, what? Okay, so we need to figure out if it's continuous at two places, two and what? And one. Okay. Well, now before we even jump in, when I see this equation, I can immediately picture a graph in my mind. When you see this equation, nothing, right? So the question is this: how do we graph this? Because we have to know how to graph these. Now, last year, I don't think you guys graphed a little bit of rational functions, no? Like this stuff where you had like a vertical asymptote and a horizontal one, like that, and the graph was look something like this. Did you graph anything like that, or do you remember?
like we did ellipses and hyperbola, but we did not do anything like that.
Okay, so we have to start now. So yeah, your regular honors, no, not honors, your regular pre-calc class, as I told you, it is much slower, but they're not going to cover everything you need to know for AP Calc. Okay, so yes, let's kind of break it down. So here, actually, let's answer the question first, and then we'll go back. Open up Desmos Graphing Calculator on your iPad, and go ahead and graph this to see what it looks like, and then we'll answer the question first, and then go back and start learning how to graph these rational functions here. Okay, so do you finish graphing?
No.
Okay, so make sure you use your parentheses for like the numerator, 2x
Oh,
plus 1, and then divide that by 2x squared minus x minus 1. Ta-da, there it is. There it is. You see that?
okay.
Okay. Now, the calculator doesn't show you a asymptote, but do you see that there's a vertical line right here? Like
Yeah.
it's invisible, but the graph is not touching it, right? So
No.
let's kind of go in. By the way, if you touch just the axis, you can magnify vertically and what? Horizontally. So put it right on the axis and squeeze it, it'll do that. You see it?
Okay. Yeah.
Yeah. So I'm gonna go like that and zoom out. So notice it's at x equals 1. You see it? Right?
Yeah.
The graph just doesn't touch that line, right? Okay. So notice, okay, at x equals 1, because the letter B is asking, is it continuous at x equals 1? And the answer is
Yeah. Or no?
no. Yeah. What kind of a discontinuity is it then?
No.
Yes, very good. And so it is not it's not continuous at x equals 1. What about at 2? Is it continuous at 2? Just at 2.
Uh,
Yeah. What's the y value at 2? Like, touch it with your finger. Oh, it's not showing. Yeah, there it is right here. See it?
oh.
Oh, I can't hold it. It's so weird. Like I was trying to hold it down, but it was so like frustrating. Anyways, so yes, if there's a y value at 2, it's continuous. A limit exists. Okay. So yes, the answer is yes, it's continuous 2. No, it's discontinuous at what? At 1. And there is what we call an infinite discontinuity. Okay. All right. Actually, let's do a couple more of these, and then we're gonna go back and graph these. Try this one. All right. Okay, so graph this one, and tell me if it's continuous at 1 and at 2. Now, I think the graph should look like it's very similar to this. X minus 2 divided by x squared minus 4. Boom. Look at that. Beauty. Okay, so answer. Is it continuous at x equals 1?
Yeah.
Yeah. The limit exists. The y value also what? Yeah, I'm only looking at x equals 1 right now. Right over what? Here, right? Yeah. So if you approach 1 from both sides like this, they both approach the same y value. And the y value, the limit value and the y value at 1 are exactly what? The same. There's no hole there. Okay. What about at x equals 2? This is actually a trick question. Ooh. This one is actually very, very tricky. Now,
It does.
okay, okay. Visually, you're like, I see, but grab your Apple Pencil, give me the y value at 2. Touch it, touch the graph, and tell me what the y value is at 2. And you'll be surprised. It should say UND, undefined.
Oh.
Do you know what that means? It means there's nothing there. Because watch, look at the original equation. If you plug in 2, what do you get on the denominator? It's 0. Now, you're asking, well, why doesn't it show on the graph? Well, it's infinitely what? Small, okay? It's so tiny, but if you put your mouse here, I'll do it for those people watching the video. Yeah, I need to like really. Oh, right there! Oh, I missed it. Ah! You have to like hold it, right? And then it just disappears. Okay, so notice that visually on the graph, you can't tell. I don't know why they don't. They should update it where like if there's like a discontinuous point, they'll put it there as like a what? As like a hole. Now, this is where even a calculator a graphing calculator is insufficient, and I'm going to show you how to do it by hand, where you can immediately know that there is a hole at what? Yeah. So a limit exists, but it's not what? Continuous. If the hole is missing, we call it a removable what? Discontinuity. Okay. All right. So do you kind of see now? I'm trying to show you why it's so important to know how to graph, right?
Yeah.
Let's see. Here, you know what? Try this. Can you I kind of want to save it for a little bit toward the end. We're gonna graph a lot, but here. Okay, try this one. Okay, can you graph this?
All three functions?
Yeah, I'm gonna try to graph it on the graphic calculator, but well, I'll graph it by hand too. But try it. Try to graph it on this page, using the grapher. I mean the graph paper, the digital graph paper. Okay, and I'm gonna try to graph this. I'm trying to figure out if, how do I? So x plus 2. Right. Huh. X. There's a way. I don't know how to do it. This x greater than equal to. Nope. Not it. How do I do like conditions here? Maybe this one. X. Wait. Cannot use inequality here. Okay. There's a way to graph this with the conditions, but I don't know how. So I have to rely on my hand. Okay. Is this your graph?
Yes.
Did you not consider any of this stuff at all? This stuff?
Oh.
Okay. If you're only graphing these, yes, it's actually right. That's pretty good. But you have to graph it according to the condition laid out like this. You have to graph an x plus 2 for everything less than or equal to 0. So what does that mean? You're only going to show this part of the graph, right? What? Here, you're going to erase that part. Wait, do you get that?
Yeah.
Yeah. What about the second part, the y equals 2? You're only going to graph that from 0 to what? 0 to 1. By the way, your wonderful straight lines was pretty impressive. Yes. Okay, but you have to graph y equals 2. Your y equals 2 was infinite, right? Negative infinity to positive infinity. But the condition, look at the condition. This is your domain. They only want you to graph that from between 0 to what? Yeah, without touching 0. Do you see that?
So it would be an open circle at
0.
right here.
Yeah. And then it'll go across. Well, okay, let's make this 1 right here, okay? So we'll go all the way to what? Yeah, and this is 2. See it? Okay, and this is not drawn to scale because we're scaling this as 1 and this is like 2. And then you want to graph what?
X squared plus 2.
Now,
Yeah.
Okay, so this is the parabola, yeah. But we're not going to graph anything less than 1. So we want to do greater than or equal to 1. So if this was the graph, then you'll graph it from here and erase all this. And you did it in yellow, so it'll be like what? See that? Like it would be like this, right?
Yeah.
But we're only going to graph everything greater than what?
1.
Greater than 1. Now, think about it. Is this graph a function? Well, how do you know if it's a function graphically? If it passes the
line test.
vertical, yeah, it passes the vertical line test. It only touches one here, once here, right here. It touches this one, but not what? That one,
Okay.
and just keeps on going. This is called a piecewise function. You see it? Okay,
Yeah.
now the question is this. Looking at this graph, when do we have discontinuity? Where? Give me the x value. It is discontinued at x equals. Very good. What kind of discontinuity is it? Jump discontinuity. Great job, Brendan. Good job. Okay. All right. So does it make sense?
Yeah.
Yeah. But now you realize you have to be really good at what? Graphing. Okay. All right. One more, and then we'll just look at some rational functions. All right. Can you graph that? Nice. Very good. Uh, Wait, are you gonna keep the arrow there, or will it stop at 2? So what you can do is you can plug in 2 into the equation, which is 5, right?
Yeah.
So go to 2 comma 5 and put a dot there just to indicate that's where it's gonna stop. And it'll just be like a curve, like a curvature. Get it?
Oh. Okay.
Yeah. And then now to graph this one, just plug it in. Plug in 2, you get 5. So go to 2 comma 5, and you put an open circle, right? And then you'll apply the slope. What's the slope? -1. So from that open circle, go down 1 over 1, down 1 over 1. No, to the right. Down 1, right 1. Because it's negative slope.
Oh, right.
Yeah, and then just trace the line that way. Okay, so do we have any discontinuity here? Where?
At x equals 0.
At x equals
Yep.
0. Very good. Okay. All right. Whew. Excuse me. Okay, so we're gonna park the continuity, discontinuity stuff here and work on graphing, and then we'll come back to this. Okay. All right. So here we go. We need to graph rational functions. Now you know how to graph all the other ones like parabolas, you know, absolute value functions. Actually, do you remember radical functions like this? Do you remember how to graph this?
Oh,
Okay.
no, it's actually
Here.
the
Now reason it out. Reason it out. You're taking the square root of a number. Yes, very good. Can you take the square root of anything negative? No. And then the square root of a number makes it really, really small, right? Like if you plug in 100, let's imagine you plug in x equals 100, what's your y value? Yeah, so you're not going to go up that high, but I mean, you're going to slowly increase, but not that much, right?
Yeah.
Okay, all right. Now we have this thing called a rational function. And a rational function, the word rational is a fancy word for it's a fancy word for
Uh,
what's a ratio? Such as an f. FR. No, fragment, okay? No, I'm just kidding. It's fraction. Yes, fraction. It is a fancy looking fraction, all right? Functions have like variables, right? So, no, well, not all of them, but so you're going to see something like this. All right, see it? You have a numerator and a what?
denominator.
Yeah. Now this is not a rational function. So this one, what kind of function is this one? Yes. It's a quadratic what?
Oh, quadratic.
Okay, how do you know it's a quadratic function? Yes, x is squared. But hey, isn't there a fraction right here in the front? Isn't that a rational function? No, it's a rational function when you have variables on the what? The denominator, okay? You have variables in the denominator. All right. So whenever you have rational functions, you always have to look for two things: the horizontal asymptote and the vertical. Okay. All right, hold on. All right, so we're back to our regularly scheduled program after these messages. I mean, these messages were already passed. Okay, so two things: horizontal asymptote and what?
Vertical asymptote.
Okay, the vertical asymptote is actually a priority, so you want to find this one first. I should have put number one there, which I will find. Boom, one and what? Okay, now to find vertical asymptotes, all you have to do is look at the denominator. Okay, look at the denominator. So here we go. I'll write it again. Y equals 2x minus 1. Okay, so what you do is when you have something like that, and you can do the next one, uh, first you write this VA, okay, it's for vertical asymptote. And you look at the denominator and ask, what's gonna cause the denominator to become a 0? Well, x equals, yeah, so this is your vertical asymptote. Okay, you never want to plug in -2. That's why there's a vertical line. No graph is gonna be on there. And then you look at the horizontal what?
Asymptote.
Yeah. Now, when you do a pre-calc, honors pre-calc or honors algebra 2 trig, teachers will give you like a 3-step like test. Okay. They'll say something like this. Look at the exponents on these. See how it's x1 to x1? When the exponents are the same, all you have to do is look at the coefficients 2 and 1 and just divide it. So 2 divided by 1 is what? 2. So you say y is equal to what? 2. But that's not the way you want to learn it because it just becomes like a do this and bam. In calculus, you actually have to know what's going on, right?
Yeah.
So here it is. Horizontal asymptote. Well, you want to look at it like this. What would happen if you were to plug in infinite numbers into what? Into the x. Yeah. And what number would they approach? So it's like this. Okay, here's a graph, and you have one, two, three, dot, 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 and you have positive what? Infinity. Okay, now infinity, it's going to be huge. So it's going to be like 100, 200 million, trillion, 4 million, trillion, billion, trillion, quintillion, googolplex, whatever. Okay, so the question is, if you were able to plug in the biggest number down the line, what would happen to this fraction? Can you see that it's going to become 2? What cancels out? Okay, so here, let's try. Yeah, you're on the right track. So we're trying to think like intuitively here. So like if x equals, let's say like 1 billion, right? So 2 times 1 billion is 2 billion. Would the minus one make a significant dent in the value of 2 million or 2 billion? No. So basically, negative one just kind of fades away. And then we plug in the same value on the bottom, which is 1 billion. 1 billion plus 2, I mean, is it going to be that significant? So basically, you're doing 2 billion divided by 1 what? Billion. What number is that? It's 2. Well, what about billion, billion, trillion, trillion, right? By that, when you plug in all those numbers, the negative one and positive two doesn't really make a what? A scratch, right? Yeah, but you're basically gonna get 2 no matter what. Now, what about in the negative direction? If you plug in negative 1 billion over negative 1 billion, well, you'll have negative 2 billion on top, negative 1 billion on the bottom. You're still gonna get positive what?
Two.
Feel like a gangster. Okay. Yeah. So the horizontal asymptote now, okay, but the thing is, the negative one and positive two, it will not make it exactly 2, right?
Yeah.
Yeah. So that's why we say there's a horizontal asymptote, meaning you're gonna approach 2, but will never actually touch what? Aha. Does that make sense?
Yeah.
Now you just go like this. Here's negative 2. You draw a vertical asymptote. Here is positive 2. That those are your guidelines, your asymptotes, meaning your graph is not going to touch those. Well, okay, now the question um, is the graph going to be like this? Is it going to be like this, right? Above? Or will it come from the bottom and go like what? Go like that. Well, that's easy to tell. Just plug in a number. Plug in a number like 1. What do you get? If you plug in 1, what do you get?
Yeah.
Wait, what did I tell you to plug in? I forget. Oh my god, I literally forgot what I told you to plug in. 1? If you plug in 1, you get 2 times 1 is 1. I mean, 2 times 1 is 2. 2 minus 1 is 1. So you get 1. 1 over what? 3. 1/3. Well, isn't that underneath the 2? Okay, so once you have that dot, you know the graph will do something like this. Yeah. And then, well, on this side, what's going to happen if you plug in something like negative 3? You get negative 6 minus 1, that's negative 7, right? Over what?
One.
Negative
1.
So you get positive 7. So it obviously has to be bigger than 2. So it's going to be up here somewhere. So you know the graph is going to do what? Okay, was that hard? No, that was pretty easy, right? No, there's several different types, so we're gonna do all of them. We only have about 6 minutes left. But okay, now go to Desmos graphing calculator and let's verify that this is actually what it looks like a general sketch of it. Nope, that's the wrong graph or wrong grapher. Okay. All right, so now you can actually type in like y equals, but usually if it's a y equals equation, you could just type in the ones on the right. I'll just do y equals just so that you can kind of see it visually. 2x minus 1 divided by x plus 2. By the way, use your parentheses for numerators and denominators like that, okay? All right, so let's zoom out and look at that. Look at that. Look at that beauty, okay?
Yeah.
Look, see, the computer almost had it like ours. It's done its best, you know? But notice the -2. You see this? -2? And then what about the horizontal asymptote? Well, I'm going to zoom in on the y-axis like this to see the number 2 there. And then zoom out. Well, let me... Did you see it? How the graph gets closer on the top like this and on the bottom. Okay. All right. You get the idea now? Yeah. Let's try another one. Again, I can just make these up just right off the fly. So y equals, you know, like x minus 3. I'm gonna put here like 3x and then 9x plus 1. Okay, try that. Graph this by hand real fast. Again, find your vertical asymptote first and then your horizontal asymptote. Yes, very good, very good. Nice, nice, beautiful asymptotes there. Good. Now plot some points. By the way, an easy point to find is your y-intercept. How do you find your y-intercept? X equals 0, right? Yeah, just plug in x equals 0 to figure out where it touches on the y-axis, and that should give you an idea. So at 0, negative 1/3 will be right here, right? Negative 1/3, that's positive 1/3, dude. There. Okay.
Graph would look like
Yeah, it has to, yeah. Okay. And then on the right side, now normally it's going to be on the opposite side, but there are times when it'll be on like this. And I'll show you those later on. But again, just verify by plugging in 2, any easy number to the right. Don't make the mistake of plugging in 1. That's the asymptote, right? It's not going to work. So if you plug in 2, you get, what's that? 18 plus 1 is 19 over 3? 19 over 3, yeah. So it's obviously it's going to be bigger than 3, right? Yeah. And so the graph will look like that. And again, let's verify it with our graphing calculator real quick before we go so that everybody in the world of YouTube will say, oh, this was right. 9x plus 1 divided by 3x minus 3. Boom. Oh my gosh. Look at that. The computer almost had it as good as yours, okay? All right, got it? Okay, for your homework, I'm going to give you some rational stuff like this to graph, and then we're going to look at other types of that as well. Okay.
Okay.
I know you have a lot of sleeping to do for the next few weeks. Try to give a little bit of your sleeping time to homework. All right. Have a good weekend. Bye.
Thank you. See you next week.